Since I can't be at school today, I thought I would leave a little video so that we would not fall behind and could keep working toward what we're looking to do with an acid-base test sometime at the end of next week or the following week. Only 3 topics I'd like to cover for class today. First, a little bit of an acid naming review from yesterday. And then I'd like to talk about conjugate acids and bases, types of bases, and then something I call ID equations, where we label the different parts of a chemical equation. So, a little bit of review from yesterday. We went through some different aspects of acid naming, and if you flip back to your acid naming table in your notes, we can work our way through these. First thing you want to do, if you're looking at a formula, you have to get yourself to the old name. So if I looked at this and named this the old-fashioned way, I would call this hydrogen bromide. Hydrogen bromide is an IDE ender. Right? So with an IDE ender, you're going to turn into a hydroic acid. So this becomes hydrobromic acid. Second one there is HBrO3. HBrO3 used to be called hydrogen bromate. That is an ATE ender. Right? So ATE endings become ic acids. So this just turns into bromic acid. Last but not least, HClO2. If we named this the old-fashioned way, you would get hydrogen chlorite. Chlorite being an ITE ender. ITE enders become OUS or US acids. So we get chlorous acid. If we jump over to the writing the formula end of things, right, with the writing formula side, right, we want to name it the old way first and then do symbols and charges and cross it. So if we have iodic acid, iodic is an IC acid. So with an IC acid, right, it is going to turn into hydrogen something 8, which will be iodate for this. And then we do symbols and charges and cross it. H plus 1, iodate, IO3 minus 1, cross those down, and you get HiO3. Hydroiodic acid is a hydroic acid. Hydroics came from IDEs, so this used to be hydrogen iodide. And then we do symbols and charges and cross it. H is in group 1, so it's a plus 1. Iodine, group 17, minus 1. Cross and reduce, and you will get HI. Last but not least, sulfuric acid. Right? Sulfuric acid is an OUS acid. Right? With an OUS acid, it used to be an ITE ender. So this used to be hydrogen sulfite, which would be H plus 1, SO3 minus 2. Cross those down. H2SO3. So, a little refresher on your acid naming review here. The second thing I want to talk about is the types of bases, which will lead us into our conjugate acids and bases. So take a second, finish copying that down. I need to let somebody in the room. And when it comes to types of bases, what I would like to do is break it down into the categories, just like we did in class when we were learning about our acids. And so with the types of bases, first type of base we're going to learn about is called the Arrhenius base. Arrhenius acids put a specific ion in solution, and that made them who they were. Right, so an Arrhenius base does the same sort of thing. We define an Arrhenius base as any substance that places OH minus ions in solution. In any substance that places OH minus ions in solution. A good example of an Arrhenius base would be something along the lines of KOH. KOH, whenever it gets placed into water, breaks up into K plus and OH minus. So because KOH is the source of OH minus ions, and if you remember, OH minus is the hydroxide, that makes KOH our Arrhenius base. One that would be a little less conventional, where you don't see the OH, could be something along the lines of NH3, which is ammonia. Sometimes substances just break apart to give you the OH minus, and it's there and you have it, and that's why it's a base. Sometimes it creates the OH minus on the product side by removing an H from water. And what happens is NH3 looks like this, with its free pair of electrons. It will go and take away one of the H's from water, and what you end up with is NH4, which will be a plus charge, and OH minus. Right? So a substance doesn't have to possess OH in its formula to be an Arrhenius base. Right? Sometimes we will take things that are able to take a hydrogen from water and then lead to OH on the product side. Just like with acids, Arrhenius bases are the most specific. Right? They are the most specific of the three types of bases that we will talk about. The second category of bases that we're going to look at are our Bronsted bases. And a Bronsted base is very similar to a Bronsted acid in the sense that it has to do with protons being transferred, right? But it's the exact opposite. A Bronsted acid was a proton donor. A Bronsted base is defined as a proton acceptor. So if we were to look at a generic chemical reaction, right, we could take something like HCl plus H2O going to H3O plus Cl minus. Now, if we wanted to go through an entire base checklist, could we say, is there an Arrhenius base? Because neither of these is OH minus. The answer to that question is no. And then we would move on to, is there a Bronsted base? And for the check in a Bronsted base, what we need to do is find a substance that on the left side has one less hydrogen than it does on the right, just like the reverse of the acids. So in this case, if I were to label things, I see HCl here, I see Cl minus over here. HCl gives away a hydrogen. That is why all that's left is Cl minus. That's not a proton acceptor, that would be your proton donor. That's why HCl is your Bronsted acid. You could either do process of elimination to realize that H2O is your Bronsted base, or you could say H2O becomes H3O. How do I go from 2 H's to 3 H's? I must accept a proton. So H2O is the Bronsted base. If we took a look at another example, I could come back with something just like what we had over here. NH3 plus H2O going to NH4 plus OH minus. In this case, do we have a Bronsted base? We will check. Do we have an Arrhenius base? We will, because we have OH minus. So if we go over here and look, what we want to do is find something that has one less hydrogen on the left than it does on the right. Right? And if you take a look, NH3 becomes NH4. Right? When NH3 becomes NH4, it accepts a proton. That means that NH3 is our Bronsted base. So if we go back and check to list our acids as well, we said HCl becomes Cl minus. That's our Bronsted acid. And in this case, H2O becomes OH minus. It donated a proton, which means H2O was the Bronsted acid. And the reason I highlighted this and chose these two examples is to show you that water can behave both as an acid or as a base. In substances that have the ability to behave as acids and bases are what we've referred to as amphoteric substances. And an amphoteric substance can either donate a proton or it can accept a proton. And when it does that, you get two different resulting chemical solutions. So those are our Bronsted bases. Right? Lewis bases will be very straightforward, right? Because when we went through the Lewis acids, right, we learned what the characteristic was. Right? So with a Lewis base, we will define it in the opposite way as we did our Lewis acid. A Lewis acid was an electron pair acceptor, which means a Lewis base will be an electron pair donor. Usually the best way to identify a Lewis base, though, is to narrow it down by identifying something as a Bronsted base or as an Arrhenius base. Because just like with the acids, Lewis is the broadest definition. So it's the least specific. Bronsted is the middle. Arrhenius is the most specific. So as soon as you identify something as a proton acceptor, you also know that it would be a Lewis base. For instance, right here, right, as I look up, is there an Arrhenius base? No. Right? Is there a Bronsted base? Sure. H2O gains a proton, goes to H3O plus. H2O would be not only the Bronsted base, but also the Lewis base. It is an automatic. If we drop down to here, we would say, is there an Arrhenius base? Yes, there is, because there's an OH minus producer. Who creates the OH minus? Right? NH3 does by accepting a proton from OH. So NH3 is the Arrhenius base. If you weren't good at spotting that, no big deal. Right? The Bronsted base is the thing that picks up a proton. So that is why NH3 was your Bronsted base. And then through process, right, of priority, Arrhenius, Bronsted, Lewis, because this is the Bronsted base, we know that it is also the Lewis base. Right, so these are the three definitions that we'll have of our different bases in terms of what's going on with that. Last thing I want to do, right, is start to talk about these things on the right side, because we focused on the left side of the equation, right, the entire time. Right, and we used the right side to make some decisions. For instance, we kept saying, oh, HCl becomes Cl minus. So we can see that these are linked. That NH3 becomes NH4. So we see that those are linked. Right, well, I'd like to give that a name. And so create a new section here. Doesn't have to be a new page. And call this conjugate acid base pairs. Right? Conjugate acid base pairs. And the whole idea behind conjugate acid base pairs is that we want to give names to what these species on the right side of the equation are. So let's tackle them one at a time. First one, the conjugate base. Right, the conjugate base gets linked to the acid. Right? The conjugate base gets linked to the acid. Right? The conjugate base, by definition, is the species that remains after the acid donates a proton. The conjugate base is the species that remains after the acid donates the proton. Right? The other half of this would be the conjugate acid. The conjugate acid gets linked to the base, and by definition, the conjugate acid is the species created when the base accepts a proton. It is the species created when the base accepts the proton. So, if you're going to take a look at a couple equations, we don't need to recreate anything new. Just recopy these two equations that we have here. Right, first one, right? HCl plus H2O going to H3O plus Cl minus. And the second one, NH3 plus H2O going to NH4 plus OH minus, right, for the second equation. So what we want to do is come in and try to label our conjugate bases and conjugate acids. They will always fall on the right side of the equation. Right? The conjugate base, the conjugate acid will fall to the right. So, if I know who my acid is, right, if I want my conjugate base, I'm going to find the thing that is linked with my acid. Right? HCl, we keep saying, gets paired with Cl minus. So here are my link. Now, you can see by definition why Cl minus is the conjugate base. Because the conjugate base is the species that remains after the acid donates a proton. So here is my acid. When it donates a proton, all that's left is Cl minus. That is why Cl minus is the conjugate base. If a question asks you, what is a conjugate acid-base pair, they are asking you this: who gets linked with who on the opposite side of the equation? So you would say HCl and Cl minus are a conjugate acid-base pair. On the reverse side, who then would be my conjugate acid? Right? H2O becomes H3O. So these two are linked. And the reason why it's the conjugate acid is the species created when a base accepts a proton. Here is my Bronsted base, because it's my proton acceptor. What does it look like after it accepts an H? H2O becomes H3O. That is why this is the conjugate acid. So it's easy to spot, right, so long as you compare them up with their partner. Now, our race, what we've already described, so it would be like looking at one from scratch. Right? And if I looked here, it's very easy to spot the pairs. Right? Who looks like NH3? Well, it's the NH4. So these two are going to be linked. Who looks like H2O? H2O is a little trickier, right? Because it could be H3O, it could be OH minus, it could be a couple things. Right? But if you save H2O for second, it becomes pretty clear that H2O gets linked with the OH minus. And so there's our conjugate acid-base pairs. Now we just need to identify acid, base, and then conjugates on the right side. So, first thing I do is I find my proton donor. NH3 becomes NH4. It's accepting a proton, right? So, if it accepts a proton, that means it is my Bronsted base. H2O goes to OH minus. There's a proton donor. That means this is my Bronsted acid. So you can either do it by opposite wording, knowing that the acid gets the conjugate base, or you can think through it using your definitions. Right? The species that remains after the acid donates a proton. Here is my acid. When it donates a proton, what's left? OH minus. That means this is my conjugate base. And then for my conjugate acid, it's the species that is created after the base accepts a proton. Here is my base. What did I create? It was the NH4. Here is my conjugate acid. So we'll save the equations for when I get back, just because I don't want to run it too close to the bell. I do a little bit of review on these things just to make sure that you guys fully understand everything that's happened. Right, there's a homework assignment over on the board. Right, with the time that's left, go ahead and get as much of that done as you can, and whatever you don't is due on Monday when you get back. Friendly reminder, you can't see it off the screen here, but page 477, 1 through 9 is due by the end of the day today.